Okay, so thank you. I appreciate the opportunity to kind of talk through things here. Yeah, I'm talking about an analysis of Starlink operations that I've continued to do based on Starlink's publicly available data. I discussed it previously last year around about November, and so this is just kind of an update on what's happened since then. There's three main kind of focus areas. One is the first is just a brief update. What's really changed with the constellation since then, since November, and then a big focus is really going to be the Starlink intra-constellation conjunction analysis. How is Starlink managing and mitigating conjunctions between their own spacecraft? That's kind of been my primary area of interest with regard to their operations, and so it's something I've been just kind of keeping an eye on. And then just kind of lastly, since this is the Free Flyer Expo, I have a handful of two examples of kind of some pretty helpful script usages that have really made parts of this analysis easier and kind of more tenable. Quick disclaimer up front that all of this is open source data that I'm using, and it's publicly available TLEs that are available via Celestrack. It's known as the supplemental catalog, and they've all been generated from SpaceX EFEMs, Celestrack does the fits with SpaceX's express permission. And Celestrack also conveniently provides RMS values for the TLE fits, which is helpful in kind of understanding each individual TLE's accuracy. And then as before, questions go in the chat and we'll hit them at the end. So here's a high-level overview as of yesterday. There's roughly 61 out of 72 planes are populated with at least a few satellites. Most have kind of the 18 to 20 range of satellites. Several have more. A bunch still actually have less. There's a couple. There's one with 2, a couple with 8. They're just continuing to deploy it, and this is just a kind of a top level visualization that I created to kind of look at, to just see what's going on at the highest level. And then also one of the important drivers for conjunction analysis is actually the number of plane crossings that the constellation currently has, and so you can see a count of that at the bottom of this display. With 61 planes, the number of plane crossings comes out to 3,660. And then I'll get more into this later, but there are a number of non-maneuverable satellites up at the mission altitude already, and I'll discuss that specifically with respect to CA. Again, as of yesterday, the plot is just kind of a view of the altitude of all the satellites that are currently in orbit, with their apogees and perigees as separate lines. They're basically color coded by launch, so each kind of color grouping is its own launch. And you can see that the vast majority are already up at the mission altitude around 550 kilometers. The band on the lower right at 350 is satellites waiting in their parking orbits. And then you can see a whole bunch of other stuff kind of somewhere in between. And the majority of, so there's kind of an interesting bifurcation on this, in that most of these kind of onesies and twosies satellites that are below a TLE index of about 850 or so, most of those are either kind of anomalous or doing some sort of like one-off experiments, or or they're actually being deorbited. So the stuff on the left is kind of going down, and pretty much everything that's in between the parking orbit and the mission orbit on the right is going up. And so, I mean, right now, you know, it's just shy of 200 satellites are actually raising their orbit to the mission orbit, you know, which is a crazy, you know, amount of maneuvering satellites, you know, compared to typical operations. And then there's another 200 just waiting to go. They have enough launch to complete the constellation, but obviously they gotta raise them to the orbit in order to do so. Another way to look at it is you know, in sort of a RAN view, which really kind of shows you where the gaps are in the plane deployments, and with this you can also see you know, which satellites are kind of targeting which RAN slots, you know, and so you know, the surface of the Earth is essentially at the center of this polar plot, and the black line is the mission altitude, and you can see all the different plane numbers, you know, that I've marked on here, and so you can see this group of, you know, purple satellites is on its way up to plane slot 54, you know, and then likely, you know, the group down below at 350 will start another step soon to kind of go and catch up to plane slot 52. So yeah, you can just kind of see this is kind of a good view of from a RAN perspective of what they're doing. And then kind of the last way of kind of looking at the status of the constellation is how are the satellites distributed within the planes. You know, you can't really see that very well in any of the other views I've shown so far. And so if you look at this sort of unwrapped view where across the bottom is essentially a, you know, co-rotating RAN. So this delta RAN of 0 is the first plane that they put up, and then, you know, and then all these other vertical lines are the other plane slots. And then the y-axis is the argument of latitude for each of the satellites. So it's a convenient way to see how they're spaced, you know, how each plane is spaced out within its orbit. And you know, from this, it's very easy to see how they're handling their satellites. You know, the nominal configuration is at this point is 18 satellites per plane. But you can see that from the numbers across the top, many of these planes have 20 satellites in them. And if you know, look closely at them, if you look at plane 3 right here, you can see it actually has 20 satellites, and 2 are doubled up essentially. So they have 2 on orbit spares that are kind of doubled up in a slot, and they keep them at a standoff distance of about 600 kilometers from each other. But then you can see there are some other kind of anomalous things. You know, you can see that for the plane at delta RAN of 150, there's kind of a bunch of satellites that, you know, there are multiple open slots, even though there are technically 21 satellites in the plane. These may be you know, drifting for RAN. You can see their RAN is off a little bit. They might be drifting back. It's hard to say exactly what's going on with these, but the satellites are at the mission altitude, so I include them in here. And then you'll also notice this little cluster over here. People probably heard of the Transporter 1 Falcon 9 launch a while ago. It actually included multiple, I think it was on the order of 40 or 50 Starlink satellites as well. And the interesting thing about this is they actually injected those above the Starlink constellation altitude and lowered them back down. And so this group here is slightly above Starlink, the nominal altitude, so that the RAN can drift back a little bit into the appropriate slot exactly. And because they didn't go through the normal orbit raising, they haven't spread the satellites out yet. I'm not sure when or how they will, but once the RAN gets closer where they need to be, I'm sure they'll just kind of drop them down and use that small SMA change to spread them out. And some of these anomalous ones are associated with the reconfiguration, which I'll mention in a second, where SpaceX kind of reshuffled a lot of the satellites and they kind of left some behind. And so I'm not sure what their intention is with those satellites yet. But this is a very, very convenient way to, again, to kind of show both the RAN gaps in the constellation and the mean anomaly or argument of latitude gaps, so you can see kind of what are the remaining slots they have left to fill. But as you can see, they've made a lot of progress. They're surprisingly almost done already after just about a year and a half of real deployment. And so, yeah, I just mentioned reconfiguration. And so what that was is kind of in late November, starting in late November 2020, around the time they released the the beta service to select users, they put out an announcement saying they were going to shuffle around some of their satellites, and they didn't say exactly how many or how they would be moving them, but what they ended up doing was reconfigured the entire constellation, and they lowered the semi-major axis of pretty much the whole constellation by 2.5 kilometers, from 550 down to 547.5. And you can see, I have some examples of how they did it for plane number 3. But when they did that, when they lowered, they also changed the number of satellites per plane from 20 down to 18. And again, they didn't release any information as to why or even that they were doing it. It just became it just became apparent that they were doing this based on the separations. And so if you look at the lower plot for plane 3, you can see the separations over time, where initially they had the same number of satellites in the plane through this whole process, which was 19 satellites. You can see in the gray series over here on the far right. And so they had 20 slots with only 19 satellites. So most of the satellites were about 2,200 kilometers apart, the standard gap spacing for 20 satellites. But then they had one open slot, which is why there's this 4,400 gap spacing here. And then they reconfigured to go from 19 satellites with one gap to 19 satellites with one on-orbit spare. So as they adjusted their SMAs separately, they started switching around their locations and got to a nominal separation of more like 2,400 some kilometers between satellites for 18 slots. And then because of the doubled up pair here, you have this one 600 kilometer separation and one 1,800 kilometer separation for these guys, and then this separation here. And so it's pretty amazing. One of the things you think about in constellation design is one of the first things you kind of nail down is how many satellites you're going to have per plane. And so to have already deployed half of your constellation and then decide, well, let's change the number of sats per plane, that's kind of a big thing. And they knocked it out pretty quickly in, just a couple of months, really about 3 months total. But interestingly, the reconfiguration, even though they're able to kind of achieve it fairly quickly, for reasons I'm not entirely understanding, it had significant impacts on what the conjunction predictions look like and kind of what that outlook is. So we'll get into that in a minute. And so what I have here, and I'll just start it in a second, is essentially a little over a year's worth of 7-day conjunction predictions for the entire constellation. So I'll just let it go. And so this is when you you do a 7-day prediction of the whole constellation and look at what close approaches you get within basically NASA's standard conjunction assessment box, which is 25 kilometers along track, 5 kilometers cross track, 5 kilometers radial as your screening volume. And so any satellite conjunctions that come within that volume, show up as a dot on this plot. And so this is just looking at all those plots over the last year. And if you can see, there's a very large kind of increase in the number of dots on these plots. And that actually happened with the reconfiguration. It created a significant increase in the number of kind of long-term conjunctions in the constellation. It's kind of interesting to see it, in time lapse like that. But looking at those individual plots, it's kind of hard to make heads or tails of anything. So, you really have to kind of trend it over time and kind of look at different aspects of it to really start to make sense of what's going on. And so to trend the data, I ended up looking at 4 different trends over time based on the conjunction data that I was collecting. So with each 7-day prediction, I look at 4 different trends, and I've got them color coded based on the series for the remaining plots that you'll see on the next several slides, where kind of the orange is the standard NASA conjunction screening of 7 days, 25-kilometer box. But then also I looked at some other boxes that were somewhat arbitrary, and I'll kind of get into them in a little bit. The 7-day, another 7-day screening, but with a smaller box of just 5 kilometers along track and 1 kilometer radial, 1 kilometer cross track, and then 2 shorter boxes that correspond to a shorter time period of the other boxes. So a 3-day box with 25 kilometers along track, 5 radial and cross track, and then a 3-day 5-kilometer long track with 1 kilometer radial, 1 kilometer cross track, which is the purple lower box down here. The 5-kilometer box was basically, boxes were just basically based on the fact that with these satellites, Starlink's operating, or SpaceX is operating both of them, so they know the OD for these things pretty well. They're all using GPS receivers and they have good OD solutions. So they don't necessarily need to worry about a 25-kilometer box, especially over a shorter time period. And the 3-day time period is really driven by kind of what you can kind of, the pattern that you could kind of see in the video, and you can see it here in this plot as well, that there really seems to be a marked difference between the amount of conjunctions after about 3 days versus before 3 days. I don't know why. I don't have a definitive answer for why this comes to be. I suspect it has to do with the way they are doing their conjunction mitigation. I think they're really only worrying about a shorter time frame and counting on being operationally responsive. But that's just a theory of mine. Other than this kind of demarcation in the data, there's no real explanation as to where that demarcation comes from. It's just a theory of mine. But because of that demarcation, that's why I separated the predictions in 7 days and 3 days. And so so how do these different conjunction outlooks over different times and for different volumes, how does that trend over time? And what you see is this plot here, and I'll take a minute to explain it because there's a lot on here. This is, starting from last March all the way through yesterday. This is all the, each one of the, all the dots that fit in the orange box on any given day is one of these points. And then the orange line is a 7-day trend line for the data to kind of smooth out some of the noise. And so, each of the other, and so the worst of the worst box, the 5 kilometers in 3 days is purple again, and again it's got the same 7-day trend line. The other parts of this that are important to note is each green vertical line is the approximate time that Starlink delivered a new constellation, or a new plane to the mission orbit, and got it into the official constellation. And so you can see the number of total planes up here. You're at 61 at the very end, just basically a week or so ago. And then this blue line here is the number of orbit crossings associated with the number of planes. So each time you add a new plane, you get a certain amount more orbit crossings. And importantly, this is it's really a quadratic process. And so since the orbit crossings are really the only places where you can have a conjunction between the Starlink satellites, as you add crossings, you add opportunities for conjunction. So, at some level, you would expect the two to be somewhat, the trends to be somewhat related. And for the longer term, the 7-day trends, you can really see that it really does that. The green and orange, it really follows that. With, of course, one very notable exception, which are these bumps in the long-term predictions. And these very neatly coincide with the beginning and end of the reconfiguration of the constellation. This is late November last year, and this is kind of mid and February of this year. And so you can see that, when they reshuffled them, they created a lot more, further out in time conjunctions. And there was, less of an increase, but there was a notable increase in both of the short-term predictions as well. And if you ignore the bumps associated with the reconfiguration, you can see that really broadly the orange, green, and red trend lines are all pretty broadly in line with this quadratic, process of the number of plane crossings. But the purple is not. It's, it's much more, it's kind of gone through some periods of kind of ramping and then kind of, stasis and kind of steady state. You can see that it's been holding about, at about 100 conjunctions predicted for each, 3-day, 5-kilometer prediction for the last, couple of months. And it's starting to trend up more recently as they've added a bunch more planes. But this clearly is not as quadratic as the rest. And in my mind, again, I only have this data to kind of hang my head on, but that obviously Starlink is mitigating their conjunctions. They're not letting them run into each other, but we don't know exactly how they're doing it and what their risk tolerances are or anything like that. But this clearly, I think, shows that there is some level of mitigation that's happening, for these conjunctions that are kind of the worst of the worst, which of course makes sense. And so, by looking at, this kind of breakup of all the different data, I think you can kind of get a feel for, they're not really worried about, conjunctions 7 days out. They're just not, there doesn't seem to be any sort of control or worry about them. So we can break this information down a little bit further by also considering the non-maneuverable spacecraft. And I'm trying to be careful about terminology because in a sense, it's kind of hard to say exactly what is a failure versus non-maneuverable. And because SpaceX has deorbited many satellites that they have delivered up to the main constellation and then brought them back down. So I think clearly they had some sort of failure, but maneuver control was not part of that. They were able to maneuver them all the way back down and deorbit them. So it was, likely some sort of, failure in the communications payload for the internet service. But there are many satellites that appear to have failed at the mission orbit and are non-maneuverable. Some are definitely failed in that SpaceX no longer produces EPEMs for them, and so to know where they are, you need to rely on the 18th Space Control Squadron's tracking of them, and you can get the data for those from spacetrack.org, and others. they seem to, SpaceX is still producing EFEMs for them, but they're not maneuvering. It's very clear from some of the trends that they're not maneuvering. So perhaps they still have some comm. I don't know, but simply the fact that they're not maneuvering means they behave differently than all the other sats, and that has impacts on CA. So whether or not they're actually operable or not, it doesn't really matter. They're non-maneuverable. And then interestingly, I'm not going to say for sure yet because it's still pretty early, but it seems like a 17th satellite has failed this past week, satellite 1348. It just seems to have died, and SpaceX is no longer producing an EFEM for it. So maybe it'll come back. Sometimes they come back after a few days, but the TLE was stale for more than a week, and then it stopped being produced altogether. That's the pattern of a failure usually. So we'll see. I'm not saying for sure, but it seems pretty likely at this point. And so if you look at the amount of conjunctions just based on some of these failed satellites, you start to see some really interesting patterns. So here is one particular satellite, Starlink 1126, which was put up fairly early, one of the early launches in the constellation, and also failed fairly early. It failed, kind of May timeframe of last year, I think. And the failure date in this plot is shown as the red vertical line. And then again, these orange, green, red, and purple trend lines are the same 3 and 7 day screenings with the different volumes. And you can see there's a marked difference between before and after the satellite's failure, with a marked increase in all 4 trend lines. And you see that with other satellites as well. Here's 1085. Again, it's on orbit for a while and fine, not much in the way of conjunctions. It fails, and suddenly there's kind of a larger trend in conjunctions. Sometimes the Starlink 1326 failed pretty quickly after getting to the mission orbit, so there's not really much pre-failure conjunction data because I only look at the conjunctions once you're up at mission orbit, but it got up to orbit, failed, and then you can see it looks kind of like the others. Here's one that was on orbit for a while and then failed. Again, you can see a very clear trend, a very clear bifurcation in the amount of conjunctions. And then here's another one that also was launched fairly early and failed fairly late. So you can kind of really see, what the failure does to the conjunction outlook. And then, here's one more, and I think that's the end of them. And then if you contrast that to, just what I have is kind of a random sampling of maneuverable satellites that have been launched at various times, you can see the distinction. And it's important to know that, over this time frame, the number of satellites in the constellation is going up dramatically. So you would expect some level of increase over time, and you do see that even with the actives. And again, this kind of bump right here is again the reconfiguration, and you can see that for all these satellites, there's a definite increase over time, but there's not nearly the marked and dramatic increase that you see with the failed satellites. So clearly, when and I forgot to mention this, but all the failure dates are very approximate, either based on kind of when the EFEMs stop being distributed, or for the ones where there's still some EFEM data, it's when they seem to stop maneuvering. And so you can clearly see that the lack of maneuverability creates a distinct difference in the conjunction outlook. And so, but how much, these are just a few example cases. How much does it really impact things overall? So to get a bead on that, I looked at, how many conjunctions involve the non-maneuverable satellites. What percentage of the total are they? And it's broken down into 3 categories. Either the 2 satellites in the conjunction are both maneuverable, or one satellite is maneuverable, one satellite is not, or both satellites are not maneuverable. And those correspond to the blue, orange, and green series on these plots, and the two plots on the right are the 7-day predictions. So the large box of 25 kilometers at the top, small box of 5 kilometers at the bottom, but both over a 7-day prediction. And again, you can see the effects of the reconfiguration on the 25 kilometer box. And what you see is that for the 7-day prediction large box, even though the 16 satellites are really only 1.35% of the population, they're outperforming in that they're on the order of like 8 or 9% of all the conjunctions involve at least one non-maneuverable satellite. Fortunately, the green series, the conjunctions with 2 non-maneuverable satellites, so the most dangerous ones, the ones that you can't do anything about, they fortunately those are still very rare. They're not really happening even out at 7 days, which is good. There are a few at the 5. It's a larger percentage at the 5 kilometer range, but they're still pretty rare, which is good. And interestingly, the non-maneuverable satellites are more closer to the 1% of the population of conjunctions versus the larger box. And it gets even more interesting when you look at the 3-day predictions. And so again, this is the 3-day prediction threshold, and it's the percentages associated with each of the 3 groupings. And what you see, and again, the larger box of 25 kilometers is on the top, and the smaller box is on the bottom. And again, what you can see is that for the close-in prediction, the short time frame predictions, the non-maneuverable satellites have played a much larger role than their 1.35% of the population accounts for. Now, again, it's you're looking at something as it's changing. So, it wasn't 1.35% of the, both the number of non-maneuverable satellites and number of satellites total is changing over time. So it's hard to, you can't really say 1.3% the whole time, but, clearly the non-maneuverable satellites were not 80% of the constellation, over last summer and into the fall. That's, so even at that time, even if they were 5% of the constellation, they're still way outperforming their relative, representation in the constellation. But then as you got into the reconfiguration, it flipped things. And I don't know why. I can't explain it. It's entirely possible there was some sort of operations change. They changed the way they mitigate conjunctions. I don't know. All I know is that there was this change at the same time as they reconfigured the constellation. And then the impact of the non-maneuverable satellites is most dramatic for the closest conjunctions. And for a while, you can see it was actually all the conjunction, all the close-in conjunctions. And early on, when there were only a few satellites, it was 100% of the conjunctions, but it was only 2 or 3 conjunctions, on a given day. So the raw numbers were very low, and you can see the variability in the 7-day average for these versus the 7-day average for all the other trends. Those are much more stable because of the overall numbers were higher. These numbers were pretty small, but you can see they're there. And again, you can see that there were around the time of the reconfiguration, there were multiple very relatively close conjunctions between pairs of non-maneuverable satellites. But again, thankfully, there's not that many overall. And again, they kind of drop back down to, almost 0 over time. But, and things are trending towards, the population representation. This is going down towards 1%. Hopefully, it eventually kind of gets there. We'll see, but yeah, it's interesting to see how much they've played over time. And then so hopefully that doesn't scare everybody too much. I mean, it's they're doing conjunction assessment and mitigation very differently than people have traditionally done. And so you can't really look at it the same way. But one of the nice things is their argument for being at such a low altitude and letting atmospheric drag kind of clear the space, it's really bearing out already. Even though there's there have been multiple failures, there's been no actual catastrophic impacts. And the ones that have failed, relatively early on, are already starting to decay out. Even though it's a relatively low drag environment right now. So the trends of Apogee and Perigee for Starlink 1037 that failed back in early May or late April last year, you can see it's slow, but it's decayed out. And this is also showing the new lowered altitude. So even with lowering the altitude and the significant increase in the number of satellites that it has the potential to conjunct with, as it's decayed, the number of long-term conjunctions, over 7 days has stayed relatively high, but the short-term and more dangerous ones have really started to fall away. And I think it's basically, based on the fact that there's more of a SMA and period difference that reduces kind of the overall risk of the conjunctions. And so if you look further out and with a bigger volume, it looks worse, but kind of a way to think of this is, these 7-day predictions aren't really translating, if nothing happened or a conjunction stayed bad, what was predicted out at 7 days would come to fruition inside 3 days. But since these counts are so much lower, it's really kind of not happening. So even though they're dead and not really maneuvering within the constellation, they're decaying out and the risk is going down. And so that makes me feel a lot better. And here is another example of a very early failure that has had time to decay out and really essentially get off the highway. And so I think so that makes me hopeful. As long as they can keep the other ones getting out of the way of these things, hopefully it won't be the stalled car on the 405 causing a major traffic jam. And so that's kind of the conclusion of the analysis that I've done. And just kind of the high level summary is right now they're about 77% complete with 1,001 out of the 1,296 satellites, in the 18 sats per plane, 72 planes. They're on station. Plus they've got all the on-orbit spares and a handful of others that are kind of hanging around. And then, they did a major reconfiguration of their constellation in 2.5 months. It had a big impact on CA, but they did it successfully. It's pretty impressive in a lot of ways. And the conjunctions, really it's pretty broadly on trend with the number of plane crossings in the mission orbit, with the major exception being the closest short-term conjunctions where SpaceX is doing active control and they're mitigating them, so they're not growing as rapidly, and these are just predictions. They're not actually happening, so they're being mitigated. But I have not enough data to really say how exactly they're mitigating. They've talked about their automated system. I'm sure it's probability of collision based, but we don't have any covariance data, so we have no idea really to say what their risk thresholds really look like. Clearly, it's not the same as NASA's, but again, that's okay. They're just doing things differently, and as long as they're responsible, then it'll be okay. And then finally, in kind of digging deep on the non-maneuverable spacecraft, which are really the most dangerous part, they definitely have been a driver, but it appears like they've designed the system to really be able to survive it, and they're starting to decay out. So hopefully, the decay rate is faster than the accrual rate. Hasn't really been that way yet, but it's still early, so hopefully we'll see. That's the extent of the Starlink data. Now I want to kind of briefly touch on two pieces of free flyer stuff that really help make this a tenable analysis over time, and really let me kind of reconfigure things and stuff like that as the analysis changed. So they've put up a lot of satellites, so that means a lot of data, a lot of analysis to do. And anytime you have a lot of data, if you can break it up into a series of n tasks that you run in parallel, you can reduce your runtime. So FreeFlyer really lets you set up really sophisticated processing pipelines with the runtime API, where you can have some sort of real thread pool and real tight handshaking and handoff jobs to different FreeFlyer processes. But for prototyping or for kind of something like this, that I wanted to keep a simple tech stack and not really have to worry about Python or Java interfaces or the various data representations in each language. I just wanted something simple, so I ended up I had an idea and I created a simple process pool of ff.exe instances, where all I use is FreeFlyer script and a Windows command line call, and I'll show it on the next slide. And it's been exceedingly helpful on managing the runtime of all the analysis that I've been doing for this. And the end result was really just two little procedures that I'm showing almost in entirety here. The main one being the one on the left, this get number of processes running, where you have n jobs and you want to run over m processes. And the secret sauce to it really is just this Windows command line call, where I run command line and generate a task list and have it search the task list for and it can be whatever, it's generalized by process name, but in this case the process name is just ff.exe, and it gets the number of processes that have that name and then just writes it to a text file in the mission plan directory, and then just reads that in to pass the information back, because the ff.exe process it's a fully separate process, so there's no inter-process communication using the run command. So you just dump it to a file real fast and then read it back in real quickly. It's literally a 1 or 2 character file, and you read it back in, and then you call that procedure from within this other procedure that runs your jobs. And so you build up this a string array of command line calls that you want to run. And so you can see run run commands, jobs to run, and it just goes through and runs all them, checking the number of processes, making sure that if it goes below the number of processes you want, then it kicks off more jobs. And then finally, there's a flag for letting it block until you're done. You kick off your last 5 or 6 jobs. They're not going to all end at the same time, but if you want all, you want to be sure all the jobs are done before you move on, then you just, pass in this flag, and then it'll keep checking and wait until that process number goes to 0, and then let the process move on. And I'm more than happy to provide these procedures to anybody who's interested. They're very lightweight, very easy to use, and I've found them very happy, very very helpful in running lots of jobs. And then the other piece that I wanted to mention is object references. It's a relatively new feature to FreeFlyer. It's come within the last, I don't know, 3 releases, maybe, something like that. Somebody else can check me on that. But it's a very handy way of managing your code, and it's object. They're exactly what the name implies. You create an object in script that is really just a reference to another object in script, and the operator used for that is the colon equals operator. You see it on line 19 down here in this very simple script snippet. And the basic example of this is it lets you kind of break up the data without having to reload the data or duplicate the memory or anything like that. So for a relatively simple Starlink themed example, if you have a launch group of 60 satellites, and they're all just in one bunch of TLEs. But then you want to look at, later on, you want to look at what orbit planes they populated to, and there was 20 per plane. Then you can just take, you can just do a reference assignment for, each satellite in each orbit plane, where I is the, the orbit plane number. Then you've got this orbit plane structure that's easy to use to, do analysis keyed off orbit plane versus the launch group, but you're not doing any rereading or duplicating of your data. And, the way I applied that concept on the Starlink analysis was for, slicing and dicing this large data set in kind of all the ways I wanted to look at it. I wanted to keep track of all the originating launches, what altitude group they're in, whether they're above, below, or at the mission altitude, what orbit planes they've ended up in, whether or not they're maneuverable. And, I didn't want to duplicate all that data because that would get untenable very quick for the size of this data set. So, the references allowed me to create, logical, intuitive data structures in my script that break up, things into those groups without having to do a whole lot of tortured logic and things like that anytime I want to index something. So, I go through all the different launches, and all the different satellites in each launch and, figure out their altitude. And then, if they're in my failed list, then, an entry goes into the defunct sats object. And then, if they're one of the ones that got launched into the sun sink, as with the Transporter 1 launch, then they get stuck in the sun sink formation object. So I can track those separately. And so, I do that for a bunch of different things. And yeah, the data is only in there once, but I manage it multiple ways. And you still have to be careful, but it's, it really helped me to manage the, the data in terms of, coloring between, between the views and the plots, and, which, data went into, each series. And it was very helpful. And so I highly recommend taking a look at using object references, if you're finding yourself kind of duplicating data or having trouble tracking like one particular data structure, basically. So that's everything I have. Overall, there's a lot of different useful features that made this analysis, easier and more manageable, especially as the constellation has grown. Bow-related annealing elements are great for large constellations like this. Structs in JSON, it's super handy for managing data. The socket object is what I use to get the TLEs each day, and then file system managing, where I put the TLEs and all that. The plotting, I think the synchronizing the information between the plots and the views is helpful for figuring things out. And command line makes it easy to to really kind of execute jobs and rerun things. This analysis has changed over time, and so I've rerun things in the past to kind of get old analysis back up to what I want to do now. And so if I want to rerun the conjunction analysis on the whole year and a half worth of data, I can just run a free flyer script that goes back and batch does all the jobs with my thread pool, and takes a while, but I just do it overnight and it's done the next day. And I've made it look like I knew exactly what I wanted to do from the very beginning, because my data is all consistent throughout, even though I didn't. So anyways, that's everything I have. I'll open it up to questions.
He says, "Hey team, this looks great. Can you remind him again how to make these cool graphs that you put up on the screen here? Are they made using script or magic? How do you get them customized the way that you do on the screen?"
Well, so some of it is what's still showing on this last slide. With the 7.6 release, we put in a bunch of extra convenience utilities that make it really easy to standardize your plots and views with kind of whatever sort of color palette and font theme and things like that. With just a couple of calls, you can completely change your outlook. And then I have a set of plotting procedures that I've used to abstract some of the pieces of it that they're actually delivered. I think at least some amount of them are delivered with FreeFlyer in the sample mission plans, and they're really handy for adding vertical lines and things like that. So yeah, there's a bunch of procedures that you can get, and if people want to get the latest and greatest from me, they're more than welcome to just email me or contact us, and I'll be happy to share them.
Cool. So next question is there a potential for many conjunctions between Starlink and non-Starlink satellites, or have you done any investigation into that?
So yeah, there definitely is. I mean, that's actually gotten the lion's share of attention from outside groups. There was the thing in the news about the Starlink conjunction with an ESA satellite where their automated paging system broke down, and people thought it was a game of chicken. And so there's actually a lot of potential for conjunctions with external satellites or objects, and actually, MOTAS and LEO Labs can really answer that. I haven't been looking at that because I was more interested in their operations and how they're managing their constellation. So, and it didn't seem to be getting coverage, by other groups. So that was my focus. I haven't really looked at it, but it is very much possible, and it does happen. But I can't really say how much and how risky those conjunctions end up being. I just don't know.
Okay. So since your focus was on intra constellation conjunctions, what was the closest near miss conjunction that you observed?
So that's a good question. I want to be careful how I answer it though, because it's TLE data, so it's not the best representation of the trajectory. Now that being said, it's TLE data that's based on the owner-operator EFEMs that SpaceX produces. So as far as TLEs go, they're very good fits. I'd say on the order of the RMS fit is usually on the order of 150 to 250 meters. So the TLEs are very good for looking at broad trends like I have, but I wouldn't really use them to say, oh, this one particular conjunction is very dangerous because that conjunction distance does have an error mounted and an error on it based on the fact that TLEs were used. Now that being said, it's shown many over time. It's shown many conjunctions, within a day and less than 500 meters. Whether or not those conjunctions were actually real, or based on the TLE error, or odds are, if there was a real conjunction, by the time that time came around, SpaceX had already maneuvered the satellite and mitigated them. But I've seen many conjunctions on the order of 250 to 500 meters, but you gotta put a big an error bar kind of on the order of that magnitude around those conjunctions, because it's TLE data that is not accurate enough to really say exactly how dangerous those conjunctions are. But they're not 10 kilometers, and they're not 5 kilometers. They're in the half-kilometer range kind of thing.
Oh, great. So you touched briefly on, or you talked briefly about the Transporter 1 launch. Just an hour ago, Transporter 2 launched about 88 satellites to a sun-sync orbit. Do you think that's going to have any effect on the Starlinks that are currently ascending?
I don't, probably not. I'll have to look and see. I mean, they probably, if they did it like the last one, they probably injected above, because sun-sync, you really kind of got to be above. And the 10 that they launched on the first one the 10 sun syncs, were they took them to an altitude of 560, so they're above the main body of the constellation. So I don't think they'll have any impact on the other ones that are already like maneuvering up. But I can't say exactly what they're going to be doing because I've never paid any attention to what their launch targets are. I just, once the data, the TLEs pop up for them, I just ingest them and take a look at where they're at.
Okay, and last question. So Starlink's eventually planning higher altitude shells. If the satellites in those higher altitude shells start to fail, it's going to create conjunctions with satellites through the lower shells. Do you anticipate them having to change the sort of operations of conjunction mitigation because of those higher shells?
That is, the billion-dollar question, really. I don't know. Clearly they have not come up with some, elegant flight dynamic solution that is passively safe and, and there's no conjunctions ever. Such a solution probably doesn't exist, at least not a passively safe one, but they seem to have solved it with automation, and being operationally responsive. Is the system automated enough and responsive enough to handle, additional failures drifting down through? Hopefully, I don't know. We'll have to see. I mean, I would imagine they will work to mitigate, failures at the mission altitude, and once they're, essentially things, sats from these higher shells, once they're getting older and close to the end of their life cycle, they'll probably actively deorbit them down below rather than risk them failing above. And so I'm sure that that'll be part of their ConOps to mitigate it, but there probably will be failures above and they'll drift down through, and yeah, hopefully their automated system will handle it. I don't know.